my honor to speak here. So my talk is about again about the temperature sensitivity, which is my favorite topic. And this is a work in collaboration with a number of researchers, including Professor Liu in Hong Kong UST. So basically my topic is about quantifying the temperature sensitivity, basically we're known as the Q10. And also is closely related to the metabolic theory of equality, which basically says, okay, the metabolic rate of any organism is proportional to the body mass as well as the temperature. So basically the temperature part of this, any metabolic rate of any organism is described by this called the Arrhenius equation, which is actually at least quantitatively similar to a Q10 value. So for example, usually we say, okay, the Q10 of primary production is about 1.88, which can be converted to activation energy, which is denoted as E here, to about 0.4 electron volts. So basically you can approximately map the activation energy to a Q10 value. So I don't want to spend too much time here, but the key question is whether there is a temperature sensitivity between the autotrophs and the heterotrophs. Previously, a number of studies have pointed out that there is a strong difference in the temperature sensitivity between autotrophs and heterotrophs, or between photosynthesis and respiration. So basically, when the temperature increases from 0 to 30 degrees, the primary production or the rate of autotrophic activity can increase by 4-fold. But the rate of heterotrophs can increase by 16 times. So in terms of the activation energy, the activation energy of the phytoplankton is about 0.32, and that for the zooplankton is about 0.65. Because this activation energy is actually, the effect is exponential. So if you convert to the absolute rate, that can differ like almost 4 times if you increase temperature from 0 to 30 degrees. And this has important consequence for the global carbon cycle, because as you can imagine, if you increase the temperature, actually the respiration will increase faster. Will increase faster than the photosynthesis. So this will provide a positive feedback to warming, and also the efficiency of the ocean to sequester carbon from the atmosphere will be reduced. So basically, if you this can be a very important factor if the temperature increase, the oceanic biota and also including the terrestrial biota will release more carbon dioxide to the atmosphere than they can uptake. So the question is, the temperature sensitivity is not so easy to quantify, okay? And recently, people have realized the importance of the thermal adaptation, so which basically gives the distinction between the apparent activation energy, the intra-specific activation energy, and also interspecific activation energy, okay? So most of the people, when they calculate this apparent activation energy, they just put the data together, okay, and run a linear regression. So imagine if the y-axis is a growth rate and the x-axis is the temperature. Both are transformed to form a kind of linear relationship. So using the red line shows the how we calculate the apparent activation energy. So the slope of this line is the EAPP, the apparent activation energy. However, because our organisms can include multiple species. So for example, if here each black line is a single species, okay? So actually within each species, we also have an intraspecific activation energy. So basically the intraspecific activation energy is basically how the growth rate increase with temperature within a single species. So in some cases, actually, the intraspecific activity energy can be greater than the apparent activity energy because of this thermal adaptation. So the thermal adaptation means as a species, they have been adapted to different thermal environments. So they can adjust their metabolism or growth rate to deviate from their usually the within species trend. So here, actually, the case is a perfect thermal adaptation. Basically, the different species, as you can see from the 4 different black lines here, the 4 different species have been adapted to the different temperature, but their maximum growth rate, shown as here the Ym, are the same. So this is a case of the perfect thermal adaptation. So there is a way to quantify this interspecific activation energy, which is if we calculate the intercept of each black line, and then we plot them against the average temperature of each species, we can get a negative slope. And also, if we plot the maximum growth rate here in C here, so the maximum growth rate, as I have mentioned, actually doesn't change with the optimal temperature as denoted above as the XM. So XM actually is optimal temperature. So this is again, this is the case for the perfect thermal adaptation. So this relates to the again to the thermal adaptation theory. So if there is no thermal adaptation, the different curves of the different species can collapse to a single one. They only differ in the optimal temperature, but their rising part can collapse into a single line. But if it is a perfect adaptation, this is the case I just showed. So basically, maximum growth rate don't change with temperature. But there is another case, which is called the Hotter's partitioning pattern. Basically, the clear increasing trend of the optimal maximum growth rate with optimal temperature, as denoted by the EL. But this trend is less strong than the within species. So basically, the species can show some kind of thermal adaptation, but the thermal adaptation is not strong enough to overcome the original thermal effect on physiology. So the objective of this my study is basically to understand what basically contributes to the greater apparent activation energy of the heterotrophic proteus than that of the autotrophic proteus. So here you can show a difference between the diatom and the ciliate. So usually the conventional wisdom is the heterotrophs usually have greater temperature sensitivity, which is seen from the higher value of the EAPP. So we compiled the largest ever laboratory data sets of the growth rate and temperature data on the phytoplankton and the microzooplankton. Okay, and then we estimate the each temperature performance curve. So the key element of our study actually is a very simple and elegant theorem. Here is basically we can partition the apparent activity energy into the intraspecific contribution as well as the interspecific contribution. So this is the intra. This is a variance weighted mean intraspecific activity energy, weighted by the variance of each experimental temperatures. And the interspecific activity energy is weighted by the variance ratio of the thermal diversity, which is the variance of the average temperature of each species as to the overall measurement variance of the temperature. So this is really the key equation in the study. So as we have this equation and the theoretical framework, we actually relatively easy to decompose the apparent activity energy. So if from the linear regression, we can calculate that the apparent activity energy for the autotrophs is about 0.36, and for heterotrophs about 0.65. So it's consistent with previous estimates, and you can see the heterotrophs do have a stronger temperature sensitivity than for autotrophs. But if we calculate the intraspecific and interspecific activity energy, actually, again, you can see the heterotrophs, they do show a kind of greater intraspecific temperature sensitivity than the autotrophs. But the interspecific adaptive energy is almost similar between the two. So, and this is the final partitioning table. So you can see, again, in terms of the apparent activity energy, there indeed a greater temperature sensitivity in the microzooplankton or in the heterotrophs than in the autotrophs. If you partition them into intraspecific and interspecific components, then you can see the main, most of the difference comes from the intraspecific component. So basically, is this within species temperature response that determine the difference in the temperature sensitivity between autotrophs and heterotrophs. So the key message is basically the lower EAPP of the autotrophs comes from the intraspecific component. And we develop a mathematical framework which actually can be used for many different cases of regression problems. So thank you for your attention. This is my end.